Welcome back. In this lecture, I will talk about other polymer properties like optical properties, electrical properties, barrier properties, chemical resistant and weathering of polymers. Now, we will briefly discuss about these properties, because for this introductory course I will not have enough time to go through in details for all these properties. Hence, my plan is to go through these properties quickly and briefly. If you look at this chart, we have studied how to synthesize the polymer, and then we have studied different techniques which can be utilized to characterize the synthesized polymer. And then we discussed also different properties like mechanical properties, thermal properties, rheological properties and viscoelasticity. We did not discuss these properties in details because we lack of time, and these are the properties of polymer which must be characterized before we think about any application. So, these are inherent properties in a polymer sample. Now, once we have this data, we can think about going into testing the properties of polymers relevant to product or applications. For example, we can talk about the thermal characterization other than Tg and Tm like HDT or other thermal characterization which I discussed earlier. We need to also characterize the sample fully in terms of their mechanical properties, especially the type of application it is meant to. Now, we have discussed many mechanical properties, but which properties need to be characterized completely, that will depend on the application for which the sample or the material is prepared for. We also need to be studying the rheological properties, because that will basically bridge between the polymer performance and product performance and the polymer structure. This also gives lot of ideas in terms of polymer processing. And then we need to calculate or need to basically determine all other properties like optical surface, electrical, weathering. Now, these properties need to be determined or evaluated depending upon the application of the polymer, and these properties are related to the structure of polymer molecules, which are characterized by these techniques which we have discussed earlier. So, this help us to understand the structure property relationship between a polymer molecule and a product. So, I will quickly discuss the other properties. I have already discussed mechanical, thermal, rheological properties in previous lectures. Now, I quickly go through these properties. Let us begin with optical properties. Now, optical properties is a very important property, especially for the polymer samples which are, or polymer materials which are required to be aesthetically important. For example, if we are using a bottle, then obviously if it is a clear, then it appeals more than if it is a dark. There are other examples, like if we are using several application where we require complete transparent plastic material or polymer material, then obviously transmission is a very important property for that particular sample. Similarly, we have several other aspects or different property within optical properties like transmission, as I discussed, refraction, reflection, scattering, absorption, clarity, haze, gloss, yellowish index, stress optical coefficient, bipresent, color. There are several things depending on the application we need to characterize for the polymer sample. Now, before we discuss the optical properties, we need to find out or we need to understand what happens when light travels through a material or when light interact with material. Invariably, there will be loss of intensity due to surface scattering or reflection and due to the bulk scattering or extinction. So, let us talk about the surface scattering. This surface scattering happens because of the rough surface, and this actually reduce clarity and also increase haze in the polymer sample. Similarly, loss of intensity happen because of bulk extinction. Extinction means decrease in intensity, and that may happen due to absorption, molecular absorption, which leads to color formation, or it could be due to bulk scattering, and this scattering is due to optically inhomogeneous medium. If there are more than one component and if the refractive index is different, then there will be bulk scattering, and that will depend upon the difference in the refractive index and the size of the scatterer. Let us talk about bulk scattering. Now, bulk scattering is due to inhomogeneities in the refractive index of the medium. If the medium has more than one component and their refractive index values are different, then the sample will actually scatter light, and this scattering depends on the difference in the refractive index between the scatterer and the medium, and of course, on the size in comparison to the wavelength of the light being scattered and the shape of the scatterer. For example, presence of crystalline phase fillers will scatter light. Similarly, immiscible blend or block copolymers, if we have immiscible blend or immiscible block copolymer, then there will be inhomogeneity in the medium, and as if the difference in the refractive index between the components are enough, then there will be scattering, bulk scattering. That may happen also in case of liquid crystalline polymers. Now, even single component polymers can also scatter light due to presence of spatial variation in refractive index, which might appear due to molding variation, and also the single component might actually scatter because of presence of impurities, voids, bubbles, etc., which may basically gives inhomogeneity and scatter light. We will give example. Take example of block copolymer of bisphenol A and a siloxane, polydimethyl siloxane. So, this is PDMS block and this is bisphenol A block. Now, this if the siloxane percentage is high, then this is a elastomeric polymer, elastomeric sample, because this has much low Tg and this is elastomeric component, and this is a glassy component which has a much higher Tg compared to the polydimethyl siloxane. And if it is a low siloxane, then it behaves like a thermoplastics, this dominates, and if you have high siloxane, this behavior of PDMS dominates. So, it behaves like a elastomer. Now, the refractive index of PC is PC means this part is 1.58 and PDMS is 1.4, which is having a significant difference between these two components. So, unless their domain size, the size is extremely low, there will be scattering happening if immiscible, as these two are immiscible with each other. If you compare two samples where the base is polycarbonate matrix and these domains are of polydimethyl siloxanes, in this case as you can see the size of the polydimethyl siloxane domains are higher compared to this sample where the size of these domains for PDMS domains is much lower compared to this. So, if you look for the optical properties for a pure bisphenol A polycarbonate, when these domains are not present, the light transmission for a 3 millimeter thick sample is greater than 88% and haze percentage haze is about 1%. For this block copolymer sample where the domain sizes are much lower compared to this, the transmission value is about 82%, haze is about 3%, but in this case the transmission is so low that the sample is completely opaque and haze is very high and this is opaque. So, this means that the scattering and as a result of that opacity or the transmission percentage transmission depends on the difference in the refractive index between the two phases. As if this is the difference is higher, then there will be higher scattering, and if the domain size is higher, then the scattering will be higher, and as a result the haziness or opacity will go up. Now, we talked about haze. What is haze? Haze is the percentage of transmitted light which is passing through the specimen deviates from the incident beam by forward scattering, which means only light flux deviating more than 2.5 degree on average is considered, and it characterizes the loss of contrast that results when the objects are viewed through a scattering medium. So, if you take a plastic material and view through it, the loss of contrast is related to the percentage haze in the sample, and percentage haze is caused both by surface and wall scattering, and surface scattering can be minimized by wetting the surface, which will basically minimize the roughness, and we can also use a liquid of similar refractive index of the polymer material, which will also reduce the surface scattering and as a result increase the transparency or reduce the haze. We often use the term clarity. What is the actual meaning of clarity? Clarity is the ability of the sample to transmit the fine details of an object viewed through it. So, if you are viewing through a polymer glass, then this ability to transmit the fine details of an object is related to the clarity of the polymer sample through which we are viewing, and it relates to the reduction in resolution. So, you can see this graph to understand this, this sketch to understand this. It is strongly related to angular distribution of scattering intensity. Maximum clarity is achieved by minimizing the size of the scattering center. It is also affected by the distance between object viewed and the sample, as it is related to the angular distribution of the scatter intensity. Clarity is negatively affected by light absorption and scattering. We will also talk about the terms reflection and gloss. Reflectivity is defined as the ratio of intensity of the reflected to the incident light. Both of these depends on the angle of incidence and refraction alpha and beta, and this is related to the intensity of the reflected light to the intensity of the incident light, and this is given by this expression where angle of incidence is alpha and angle of refraction is beta. Gloss relates to the reduction in the intensity of light scattering specularly of the surface. Gloss is the ratio of reflectivity of a sample to the reflectivity of a standard sample, and the typical standard for gloss is optically flat black glass. So, if you compare the reflectivity between a standard sample and the particular sample, we can measure the value of gloss quantitatively. Gloss increases with increasing refractive index, increasing angle of incidence, and gloss decreases with rough surface resulting in light scattering, optical inhomogeneities just beneath the surface, and other factors which affects gloss are polymer surface morphology, processing parameters, mold finish. For example, blending with rubbers usually lead to decrease in gloss value in case of crystalline polymers like polyethylene. There is also another term related to optical properties is birefringence. This is related to the optical phenomena in which a sample exhibits different refractive index for plane polarized light in two perpendicular direction. If we use two differently plane polarized light, and if it is so different refractive index for those two plane polarized light, then we call the sample have birefringence, and this happen if the polymer contains crystalline phases, because the refractive index will be because they are aligned, crystalline phases are aligned in a particular direction. Hence, the refractive index towards different plane polarized light will be different if the polymers have crystalline domains. For example, if I have this type of polymer for like bisphenol A, then this in this direction the polarizability is higher, whereas in a other transverse direction the polarizability is lower. So, we have a birefringent. So, in macroscopic way we can actually look for the refractive index values in two direction. If they are not equal, then the polymer sample shows birefringence. We will move to next property, electrical property, and again I will just briefly touch these properties. Most common polymers or commodity polymers are insulating or dielectric, and this is very advantageous because polymers are used for many applications as electric insulators, and as a result polymer dielectrics are used in capacitors, low conductivity charge storage device, and as a insulator which require low conductivity and should not store charges. So, typical value of polymers are insulator 10 to the minus 15 Siemens per centimeter, whereas conductor which are metals have very high conductivity values. And recently, not very recently, but about few decades back, conducting polymers were discovered and they have a conductivity value around this region, and some of these example of some conducting polymers are shown here, like polyaniline, polypyrrole, polythiopenes, and these they actually do not conduct or behave like conducting polymer as such, but when they are doped, for example, if polyaniline is doped with a proton or acidified, then it shows conductivity because of the movement of electron through backbone due to possible resonating structures. We will now discuss about barrier and permeability in polymers. This is also very important because in several cases the container must be having barrier property to several gases. For example, if we are using a vial of a drug, then if the drug reacts with oxygen, then the storage time of that particular drug will depend on how good is the vial's barrier property. If it can sufficiently barrier the passage of or diffusion of oxygen from outside to inside, then the stability or lifetime of the drug will be higher. So, barrier is very high, very important. Similarly, in some cases permeability also important. If for example, we are using for some medical applications where the polymers need to actually allow oxygen to diffuse in and out, in that case permeability is also important for polymer samples. So, barrier properties: having low permeability coefficient, restricted passage of gases, vapors and organic liquids. Increasing demand for packaging industries, preserving flavor, smell and safety or food products or even pharmaceutical products. This is very important now, barrier properties. Permeability is required for products where the solubility of gases or vapors in a polymer and its diffusion coefficient. So, permeability of a polymer sample depends on the solubility of the gas or vapor in that polymer matrix and the diffusion coefficient of the gases or vapor through the polymer matrix. And permeability measures the rate of transfer of a gas or a vapor per unit area and pressure difference across a film thickness. So, for a given pressure difference across the thickness, the permeability is expressed as the rate of transfer of gas or vapor per unit area. Higher permeability of plastics to gases, vapor, water vapor and aroma compounds compared to glass and metal food containers. So, instead of using a plastics container, if we use glass container and metal food container, then the permeability will be lower or the barrier property will be higher in general. So, plastics actually lose out or still some way to go to match the barrier performance of glass and metal food containers. So, still a challenge to be met, and there are many approaches like addition of clay type materials which increases the barrier property, and we can increase the crystallinity to also increase the barrier property in polymer sample. We talk about diffusivity. Diffusivity depends not only on the molecular structure, but also on the crystallinity and crystal morphology of the polymer sample. Higher the free volume, obviously the space is higher, so higher will be the diffusivity. Higher is the crystallinity, lower would be diffusivity, as one can easily understand. And if the path, diffusion path is tortuous, so if you add some clay materials in between, then the diffusion of the gases through the matrix will be tortuous. That means the gas molecule has to pass through way around those obstructions. So, the length of basically diffusion length will be much higher compared to a pure matrix where these obstacles are not there. So, if higher is tortuosity, lower would be the diffusion. Increase with the decreasing gas, decreasing size of the gas molecule. Obviously, this is understandable. If the size of the gas molecule decreases, then diffusivity will increase. For example, transmission rate is given in this order. As the size increases, the diffusivity comes down. Solubility of the gas depends on the chemical affinity of different molecular species, as we have seen that these two factors in combination determine the barrier property or permeability of the sample. So, if you want the polymer samples to be effective as a barrier property, we need to decrease the solubility and decrease the diffusivity of the gases through the polymer matrix. Next, we will move to the next property, chemical resistance. Now, chemical resistance is the resistance of polymers to various chemicals, and which depends on the number of criteria, which includes chemical structure, solubility of the polymer in the experimental chemical. Obviously, if the polymer is more soluble, the chemical will have chance to degrade or interact with the polymer more than if it was not soluble. Crystallinity, morphology crystallinity will obviously prevent these chemicals to interact with polymer chains, hence resistance will be higher. If they are molded in stress, that means during the molding process, if stress is built up and it is not released, then those places which acts as a kind of a crack, and when you apply external chemicals, harsh chemical, those stress will actually will basically facilitate the breakage of the polymer sample when it comes in contact with the harsh chemicals. And time, of course, the higher is the time, higher will be the or lower will be the resistance, and temperature, if the temperature is higher, lower will be the resistance. Stress, obviously, if we apply more stress, the condition will be harsh, then the resistance will also come down. Obviously, if the concentration of the chemical is higher, then the resistance of the polymer sample will be lower. And types of exposure, obviously, if it is whether you are taking the sample and immersing in the chemical, or you are just contacting, that will also determine the exposure, the chemical resistance of the sample. Now, chemical, what it may cause on chemical exposure? It may result in physical degradation, for example, stress cracking, crazing, softening, swelling, discoloration. These are the physical degradation in terms of loss of physical properties. It can also degrade chemically, that means it can decrease or it can degrade the chemical nature of the polymer, decrease the molecular weight and can react with the chemical, and as a result it can decrease the properties, good properties of the polymer. Next we will move to weathering of polymers, and weathering means there are several polymers which are applied in applications which are outdoor applications. If you are talking about a stadium, football stadium covered with polymer sheets, or plenty of car dashboard, or there are many examples we can give where the application of polymers are in outdoor application, and which as a result the polymer sample will come in contact or come in exposure with several harsh condition, for example UV radiation, visible radiation, and the extent of this radiation will of course depend upon which session, the summer or in winter, and what angle of exposure, what latitude we are in, which part of the world we are in. That will, so basically the the plastic or the polymer will behave differently at different places or different session. The other factors which causes weathering of polymers mean degradation of polymer properties, their heat, and thermal cycling, air temperature, these also cause the polymer samples to lose its good property. And another important factor is moisture. When we are using the polymers in outdoor application, then the amount of moisture in the environment will also affect polymer properties, and the amount of moisture is basically affected by the amount of rain or condensation or humidity in the medium. The more humidity, it is bad for the polymer samples, and actually the property gets degraded faster in a higher humidity environment. Other factors like acid rain, pollutants, they also actually degrade the polymer samples, and as a result good properties of polymers actually get destroyed. Sometimes mechanical stresses, abrasion also may cause damage to the polymers, and the importance of these factors are in this direction. So, decrease importance, for example, the UV radiation is very highly important for outdoor application, because of the high energy of the UV radiation, they actually cause lot of damage, and then heat, and then moisture, and this direction. And because this is a very subjective evaluation and it depends upon various factor, so weathering of polymers, no uniform test condition is applicable, and there are some indicative test conditions are suggested by different standard organization, and those are followed in laboratory. So, with this I will stop this lecture, and next lecture I will talk about the other property, few other properties.